All right, let's kick off this deep dive. We're going deep into a paper that's, well, kind of changed the game for computer vision. ImageNet classification with deep convolutional neural networks. It's a classic.
Oh, absolutely a classic. 2012, that's when it dropped, and it really showed everyone what deep learning could do. For image recognition, it was a big deal.
Huge. But for our listeners, the programmers out there who are just starting to explore image classification,
Yeah.
we're going to break this whole thing down for you.
Yeah, make it nice and clear.
Exactly. So we're talking ImageNet, but it's not just about the data set, is it? It's more about,
It's about the challenge of teaching a computer to actually see. Like, how do you even begin to do that?
right. I mean, think about it. We see a cat. We know it's a cat. Easy peasy.
Hmm.
But to explain that to a computer,
It gets complicated fast.
yes, super complicated.
Right.
So that's where these convolutional neural networks, CNNs, come in.
Hmm.
Can you, break those down for us from a programmer's point of view?
Okay, so imagine you've got a CNN, right? Think of it as a bunch of filters you're running over an image. Each layer, it's pulling out different features, and those features become more and more abstract as you go deeper.
Okay, so the first layer is all about edges and corners, the basic stuff.
Exactly. And then later on, you're picking up patterns, things like a cat's ears or tail, stuff that makes it a cat, basically.
So it's building up this understanding, like hierarchy by hierarchy.
You got it. And the deep part, that just means lots of layers so the network can learn these complex, hierarchical representations. This paper, their network, had 8 layers.
8. Whoa,
Back then, that was massive.
I bet. Must have taken some serious computing power, even for 2012.
Oh, for sure. They actually used 2 GPUs, running in parallel. It was pretty cutting edge.
Wow, pushing the limits. And of course, they had ImageNet, right? Millions of images, all labeled so many cats.
It's crucial, though, that scale. You need a ton of data to train a deep network properly. Like, imagine a programmer trying to learn a new language from just a few lines of code. Not going to happen.
Right, you got to immerse yourself in it, see all the different ways things work.
Exactly. So you got this deep CNN, powerful hardware, and a massive data set. What else made this paper so special?
Well, they had a few tricks up their sleeves, innovations, you could say.
Okay, yeah, lay it on us. What were these innovations?
So one of them was these things called ReLUs, rectified linear units. They're like neurons, but they learn way faster.
Oh, ReLUs, right. I've heard of those. But what made them such a big deal?
Well, before ReLUs, training deep networks, it was SLW. Think of it like you're debugging and you hit this infinite loop. Painful, right?
Oh, yeah, that worse.
ReLUs, they fixed that, the vanishing gradient problem it's called. Suddenly information could flow through the network, no more bottlenecks, and training sped up like crazy.
Yeah, so it's like they cleared the path, made everything more efficient. Exactly. Now programmers could actually train these huge networks, in a reasonable amount of time. It opened up so many possibilities.
Amazing. Okay, so what else? You mentioned something about dropout earlier. That
Mhm.
sounds kind of counterintuitive.
It does, right. So dropout, it's like you're randomly silencing some of the neurons while you're training the network.
Why would you want to do that?
Hmm.
It's like making the network forget what it's learning.
Think of it this way. You're building a program, and you only test it on one very specific input. It might work perfectly for that one case, but then completely fail when you try anything else.
Ah, right. So it's too specialized. Doesn't generalize well.
Exactly. That's what dropout prevents. By dropping out these neurons, you're forcing the network to learn more general features, the kind that work no matter what.
So it's like introducing a bit of chaos on purpose.
In a controlled way, yeah. Makes the model more adaptable. And it worked too. This paper, they hit record-breaking accuracy on ImageNet. It showed that deep learning, it could beat the traditional computer vision methods, hands down.
Wow, that's a big deal.
Huge. But it wasn't just about the numbers, They also wanted to understand what the model was actually learning, how it was seeing these images.
Right, not just memorizing patterns, but actually understanding.
Exactly. And they found some interesting things, like even when an object was off-center in the image, the model could still identify it.
That's pretty cool. So it's not just matching pixels, it's understanding something about context.
Exactly. It suggests that the model is learning about the relationships between objects, how they fit together in a scene. It's getting a little bit closer to how humans see the world.
Wow, that's incredible. So it's not just about building a classifier, it's like unlocking this deeper understanding of how machines can perceive the world. This is all really fascinating.
Yeah, it's pretty mind-blowing stuff.
But, okay, before we go too far down the rabbit hole, let's go back to those innovations you mentioned. I want to dive deeper into ReLUs and dropout. See how they really work under the hood.
Let's do it. We'll break down those techniques and then we'll look at some of the other cool stuff in the paper. Stick around. Okay, so real use. Let's dive into those. Think of it like this. You're coding, right?
Yeah.
And you're writing a function, want to simulate a neuron. Back in the day, you'd probably use a sigmoid function or maybe 10. They have that, smooth S shape.
Yeah, I remember those. But didn't they cause problems when you started getting into these deep networks?
Oh, yeah, big time. The problem is they saturate those functions. Like at the extremes, the output just flatlines. Doesn't matter how big or small the input gets.
Okay, so what happens when these neurons, they're saturated during training?
Well, think about it. You've got the signal, right, flowing through the network. It's carrying info about how to adjust the weights, to make the network more accurate. But when those sigmoid or tan neurons, when they saturate, the signal gets weaker. Sometimes it just vanishes completely.
Right, the vanishing gradient problem.
Yeah.
It's like playing telephone, the message gets all garbled by the end.
Exactly. Now, real use, they come in and fix this. For any positive input, the output just increases, nice and proportional. No saturation, no vanishing gradients.
So it's like this clear channel the signal can flow through, no problem.
You got it. And for a programmer, what does that mean? Faster training, deeper networks, no more hitting that vanishing gradient wall. It was a huge step forward.
That makes sense. Okay, so what about dropout? You said it's like randomly turning off neurons during training. I still don't quite get that.
Okay, so let's say you're training a model, right? Wants to recognize different code, Python, Java, C++, say, whatever. But your training data, it's all perfect code, perfectly formatted, indented, the whole 9 yards.
Uh-oh, I see where this is going.
Yeah, so your model, it becomes this expert at recognizing textbook code. But then you throw some real-world code at it, messy, inconsistent.
And it just crashes and burns.
Exactly. Overfitting, it's called. The model gets too specialized, doesn't learn the underlying principles, the essence of each language.
And dropout fixes this.
It helps, yeah. By randomly dropping out neurons during training, you're basically saying, hey, don't rely on any single neuron too much.
Yeah.
Learn those robust features, the ones that generalize no matter what.
So it's like telling the model, don't get too attached to any one way of doing things. Learn the big picture.
Exactly. It's a form of regularization. Prevents overfitting. And then, during testing, all the neurons are back online, but their outputs are scaled down a bit, to account for the dropout.
So it's like averaging the predictions of a bunch of different models, each trained a little differently. That's clever.
Right. Now, besides real use and dropout, they also use this thing called data augmentation. Remember, we talked about how they made more training data by tweaking the existing images?
Yeah, like flipping them, rotating them, that kind of stuff.
Exactly. Super valuable, especially if you don't have tons of data to begin with.
Yeah.
It's like showing the model all these variations, so it can handle whatever the real world throws at it.
So it's not just quantity. It's like expanding the variety of data, too.
You got it. And it kind of mirrors how programmers learn, right? We don't just memorize code snippets. We experiment, refactor, try different styles. It's all about broadening our understanding.
That's a great point. It's like giving the model a well-rounded education in image recognition.
Okay, so now let's switch gears a bit. Let's talk about how they evaluated the model. They didn't just, record accuracy and call it a day. They dug deeper, wanted to see what the model was actually learning.
Right, not just matching patterns, but actually understanding. We talked about that.
Exactly. And one of the things they found was that the model, it could recognize objects even when they were off-center in the image.
Really? So even if the cat wasn't right in the middle of the picture?
Yep, it could still nail it. Which tells us something interesting, right? It's not just about matching pixels. The model's learning about context, understanding that a cat is still a cat no matter where it is in the frame.
So it's getting closer to like how we see things. Understanding the relationships between objects.
Exactly. And that's crucial for all sorts of real-world applications, right? Like self-driving cars, robots, navigating environments. Context is everything.
Makes sense. You also mentioned that they use the model's internal representations to find similar images. How did that work exactly?
Okay, so picture this. Each image, it goes through the network, right? Layer by layer. And eventually, in that last hidden layer, it gets transformed into this high-dimensional vector, an embedding, it's called. And that embedding, it captures the essence of the image, its meaning, in a numerical form.
So it's like a fingerprint for the image, but it's about the content, not just the pixels.
You got it. And by comparing these embeddings, you can find images that are similar, even if they don't look exactly the same,
So like you could search for dog, and get all sorts of dogs, different breeds, poses, even if the pictures themselves look pretty different.
Exactly. It's like searching for code, but instead of keywords, you're searching for meaning. You could find two pieces of code that do the same thing, even if they're written totally differently.
That's really cool. So this paper, it wasn't just about building a better image classifier. It was about exploring how deep learning can represent the visual world,
Yeah.
in a way that makes sense.
Absolutely. And it had a huge impact, inspired tons of research, all these new applications of deep learning.
Yeah.
It really opened people's eyes to what was possible.
It's been amazing digging into all this. But before we wrap up, I'm curious about the bigger picture. Where do we go from here? What's next for computer vision, for deep learning in general?
Great question. And in our final part, we're going to explore some of those exciting frontiers. Stay tuned.
Okay, so we're back. We've been deep in the weeds with this ImageNet paper, seeing how it really shook things up in computer vision. But it's not just about cats and dogs, right?
Yeah.
There's got to be a bigger picture here.
Oh, absolutely. This whole idea, training these deep neural networks on huge data sets, it's powerful stuff. It's like a new way of thinking about programming. Let the data do the work. Build those algorithms.
Yeah, that's a great way to put it. And we touched on a few examples already, like natural language processing, speech recognition. But where else can we apply this? What other fields are ready for this deep learning revolution?
Well, let's start with something close to home for us programmers. Code analysis. Imagine a model that can really understand code, not just the syntax, but the logic, the intent behind it.
Now, that would be game-changing. You could use it to, like, automatically find bugs, generate documentation, maybe even translate code from one language to another.
Exactly. And the cool thing is, we've got the data. GitHub, open source repos, tons of it. That's what these models need, to learn and get better.
So instead of those convolutional layers picking up pixels, we'd have layers that analyze the structure of the code, the relationships between the lines.
You got it. And just like with images, you can use data augmentation, introduce variations, refactor the code, even inject some errors, make the model more robust.
That's wild. What about other types of data programmers work with, like time series? Logs, sensor data, that kind of stuff.
Time series, yeah, deep learning's making big strides there too. Instead of convolutional layers, you'd use recurrent neural networks, RNNs. They're designed to handle sequences.
So an RNN could, look at stock prices, find patterns, predict trends, or maybe analyze server logs, spot anomalies, potential security threats.
Precisely. And these models, they can pick up super complex patterns, way beyond what the traditional methods could do. It's like having a superpowered pattern detector just for programmers.
That's amazing. But I'm guessing there are still some challenges, right? Limitations to this whole deep learning thing.
Oh, for sure. One big one is data. You need a lot of it, and it's got to be good quality. Otherwise, the models overfit, they don't generalize well. Imagine trying to teach a programmer a new language with just a few examples.
Yeah, not gonna get very far with that.
Yeah.
And what about, understanding how these models work? Sometimes it feels like they're just black boxes, right? You get an answer, but you don't know why.
Yeah, that's a real concern. Interpretability. These deep learning models, they can be pretty opaque, and that can be a problem, especially in fields where trust is critical, like healthcare or finance. You need to know why the model's making the decisions it's making.
So we need more research, more tools to make these models more transparent, help us understand their reasoning.
Absolutely. And then there's the ethical side of things, too. As these models get more powerful, we got to make sure they're being used responsibly, fairly, no bias, no unintended consequences.
That's a huge point. We need to be thinking about the impact on society, making sure this technology aligns with our values.
But even with all that, you can't deny the potential of deep learning. This ImageNet paper, it was a turning point, showed everyone what was possible, and it sparked so much innovation. It's still going strong, too.
It's amazing to see how far we've come. And who knows what the future holds? Maybe we'll have models that can not only understand code, but write it too. Generate entire programs from scratch.
Or maybe AI systems that work alongside programmers, suggesting solutions, optimizing code, even anticipating our needs before we even know them.
The possibilities are mind-blowing.
Yeah.
But it all comes back to data, right? Learning from data. As we generate more data, as our computing power keeps growing, the potential of deep learning just keeps expanding.
It's a pretty exciting time to be a programmer. We're at the beginning of this whole new era of intelligent tools, technologies that are going to change how we create, analyze, interact with the world.
Couldn't have said it better myself. Well, on that note, I think we've reached the end of our deep dive into ImageNet and the revolution that is deep learning. Hopefully this has sparked some ideas, maybe got you thinking about the possibilities.
Yeah, keep exploring, keep learning, keep pushing the boundaries of what we can do with code and data.
And remember, sometimes the biggest breakthroughs, they start with a simple question. What if?